try to focus on what the speaker says. Okay, anyway, it's time. It's almost time. Welcome you all. We are very happy that you could all make it. And we have actually worked hard to put this program together. And I hope you make the maximum out of it. So do attend all the sessions. In the mornings, we have introductory lectures covering more theoretical aspects. Afternoons are devoted to hands-on sessions. And you should, you're welcome to stay here beyond 5:30, which is the official closing time, just to finish the day's task. You will all be working very hard because, we have packed a lot of stuff in these 5 days. But that's the purpose, right? So anyway, welcome you all, and let's get started. The first talk is by Professor Arkaprava Basu, who's in the Computer Science and Automation Department here at IISc and Arkaprava. Thank you.
Okay. So we'll be talking about overview of a lot of things, which essentially broadly covers everything about both CPUs and the GPUs. So you can say here, right? Yes. So it will be a very high-level overview. In the process, I'll also leave some breadcrumbs for you. So some of you are interested, you can actually follow those and get deeper understanding, and also hanging out a little bit for the lecture during the tea, so you can catch me and things that might be interesting. So as a time first, this will be a very basic overview of some of the things about how CPU, whenever I think works, what are the important aspects for it, and then also about GPUs that are often used for parametrics. With that, before we actually get started, and agenda, nothing to nothing special about it. We'll start in serial. We'll see how large server like components of it, and then we quickly touch upon the GPUs, which are like any supercomputers today. All of the work is done by the GPUs. Okay, with that, we'll get started. But before we do, this is a kind of a reminder slide that what we'll be talking about is bit of the whole in how the computer works. To manage the complexity of tens of billions of transistors in a processor, you are actually running some programs, magically works. To manage that huge complexity, the whole computing subsystem is divided in stacks, right? So you start at the very top of it, where you're trying to solve a computational problem all the time.
The screen apparently is not shared. Can you show it? I think there'll be a lot of material. So unless you have really a burning question, we can keep it till the end. It's okay. Or now it's fine.
So what we're actually talking about is that computing is engine stack. It started with an computational problem that you want to solve. Things like very basic things like okay. To solve that problem, you might have different logic that you can use to sweat which comes to happen. Okay. And once this is that, you have to actually in something that the computer understands. So human can express like C, C++, Python, you name it, right? Once that is done, there is a software called compilers that actually takes the program that a human can reason about, write, and so on, and take it something that computers can understand. So that was the bridge. Then comes this runtime system that includes operating systems and so on, is because the computer as itself needs to be managed. It has network, it has memory, it has multiple processors. Simply needs to be in control of who gets to what is running what, and so on. That's where the runtime systems comes from. Like general language runtimes like Java runtime, you also have said you would be more familiar with MP as well.
I managed it, Shoto. I won't trouble you now. Sorry.
There's a question.
I think she's not muted.
So anybody on the teams, if you are not asking a question, please mute yourself.
Thank you.
Okay. So there is this runtime. Okay. That what happens is getting into the processors. Okay. So this is the part that you can actually think of consists of the processors in the computing system. So ultimately, you compute by moving electrons, and you will have transistors, billions of transistors, tens of billions of transistors in those of these ones, which are essentially nothing but switch. There's no much more for them than me. And then on top of it, what actually consists is what's called this architecture. What is the microarchitecture? Architecture is what actually interfaces to the software. Something like, if you say an instruction set architecture, this is the language that the processor, the hardware understands. For example, you might have actually heard of x86 processors. Like both Intel and AMD's processors, they understand the same language, x86. But if you buy a processor, that's not like you have heard of ARM processors. That is a different language than the hardware understands. Okay, DSP and so on. Once that is done, once hardware understands what you're trying to actually asking it to compute, then there is a question how the processor implements it. So that goes into microarchitecture that is not exposed to the software. All the juggling that actually happens with those tens of billions of transistors inside a processor is not exposed to the software, goes into the microarchitecture. And you can have different types of processors. You have CPUs, GPUs, there are like multiple accelerators today. Like the big internet companies, they have their own favorite pieces that we Amazon, they have a Computational. If it is Google, they have some accelerators called GPUs for their machine learning and so on. So these are all processor, different OS to implement different type of things that can actually they execute. So today, what we'll be focusing on is looking at of architecture and the microarchitecture. So this is any of these like we would not be actually talking about in this particular lecture. So this is the part that we'll be discussing. So now you understand why this lecture will go. Let's take another step into what what does the computing systems typically have. Right? So if you go to the ACRC, the Computing Center here, if you go you'll probably see something like this. There is a lot of in the rank-based companies. These are actually companies. So what is that we'll be focusing on? Take a step into it. So if you open one of those out, it will look like something like this. Right. So in these slots, this is why I say CPUs go in. Okay. And there is this bunch of things here that are actually standing up. All are actually the memory. Okay. And then there is a bunch of other things like you'll put GPUs and so on here, the networking components. So in this talk, we'll be talking about a bit of how CPUs work, and then we'll talk a little bit about how, say, GPUs work. We want to make sure you understand processor is important, not the only part of computing system. And think about the memory subsystem and the DRAM which will be done today. This one is a critical. Like 40%, if you look at the data centers, 40% of the stuff and installs and different goes to DRAMs because they're not hungry, they're actually costly. Some slides to make sure you understand you are looking at a part of the computer system you are actually looking. So let's take a look. What really is there typically inside a CPU? So this is kind of a picture that's called a die shop. So if you open up this, this is outside what you actually see is the packaging. Okay, there will be pins and so on that is actually coming out of the processor in the below where you can actually put this connecting of these things. Then if you open that up, actual chip is there, and if you take a picture of this transistor, this is how it actually looks like. Okay, So it consists of a lot of things. This is the DRAM that actually connects to DRAM is on the motherboard. So you have actually to it. There will be multiple ports. This is why the computing will actually. So there is a lot of other things like in a memory controller that actually controls the memory. There will be a controller because you have to talk to the network and so on. This is on the start. There is a what we call the cache. We'll talk a little bit about that and why we need it. And then this is the cores. There are typically multiple cores in today's processor. This is why that functional computing happens. Yeah. And we will be actually looking at next is what typically happens very high level inside core. So we'll start with the very basics. So when you actually start executing a program, so first when you compile it, it's non. So that's actually a file. That's a file which one can read, scan, right? So you put it somewhere in a file system in your laptop or another. So which would typically be somewhere in the disk or your SSD. Now the processors cannot directly access anything that is on the disk. It needs somebody's help. Okay? Who is that typically? It's the operating system. So what it does is that first it brings whatever you need to the memory. Memory is data. Okay. Once it is there, it has addresses. Okay. Those addresses the processor can use to say that I need this particular data. This is in like files and so on. So I just say this is the data that I actually need. This is the there is two parts of it. One is that code that I did, and also you put them on some data, right? You come with what you look up with it also your okay, the computing, the processing of that will start is fast. You have to fetch the instruction to the processor, to the code, right? It is in the memory to start it. You have to bring it down. It's called the fetching the instruction. Because until you know what to execute, you don't know what data you would actually require for it. Okay. And so that's the first thing that you do. That's the instruction fetch. And what instructions to fetch and why it actually locates. So it's captured in something called program code. That's an address in the memory that tells you what is the next instruction processor must execute. The next obvious thing to do is that once that instruction is there, you need to figure out, what this instruction says, like what I actually do. So if you, just an example instruction, you'll actually have something called opcode that actually codes that, I'm being asked to do an addition, for example. And these are, are all encoded in this instruction set architecture that we actually talked about that a few minutes ago. But then it will have, say, something like, okay, what are the operands? Like, for example, here it is going to say that, okay, in the contents of this register are 0 and 15, you add it to and put the results in a register action. So here are the registers. These are really fast places, actually, registers where you actually keep the data that you are actually operating on. There are only few of them available for each core, and there is defined how many of them. One of these in the instruction set architecture, which is the the boundary between the processor and the system. Okay. They're fast, so you can actually quickly access them and compute all that. These are encoded inside. But the processor knows how to actually decode this. That's the part that goes next. After you get the instruction, you decode them to figure out what are my operands, why they are, what is the computation I have to do. Okay. And then you might actually fetch that operands into the registers. So that becomes operand fetch. Once you know what you have to do and your data operands are there, you need to actually execute. So it's not that you have to execute stage. Once that is done, you have to actually store back the result. The rest is you can actually store it back to the list based on, in this particular case, in this example, You're storing it to the disk, or it can be something that you can actually push it back to the memory. Okay, there are high-level 2 types of instructions, 3 types at a very high level. One is that a computation, the instruction that you do, compute, for example, add, multiplication, division, and so on. Right? Then you have an important set, which is the memory instructions like load, store, and so on. Everything, remember that everything is in the memory. Okay, so limiting to the code, okay, to the registers to actually compute it. So those are the load, as they suggest, loads and stores. Then you have control instructions too. Control, like you'll have if-else bunch all over the place in your program. Typically, every 5 instruction there will be an if-else on an average. Okay, so you have those kinds of instructions too, and then there are other instructions like control IOs and so on. But these are the kind of instructions that you can just see that not all of them actually write the results to the memory. Some of them will access the memory, some of them will not. All of that depends on what kind of instructions you're actually executing. In general, as we talked about, the instructions architecture, as said, tells the software what to and hardware what to do. In architecture determines those instructions are actually implemented. At a high level, quickly go through it, like how high level one very basic architecture within a processor, how it actually looks like is something like that. It will start with when you repair a program counter and tells what the next instruction that you have to execute is. You see this instruction cache, we will need to talk about later, but these are, you can think of like parts of memory that while the instruction could be in here. Once you have that instruction, you have to also access the operands, which in this register that we were talking about, where the first place is where you keep the operands. So that is why the instruction decode and operand fetch, typically these are actually done together. So that you actually execute. This is why this arithmetic logic unit. This is where the actual computation, whatever you need, happens. And then finally, this is why you write back the results. This is at a high level, basic things you actually do. Okay, and within that there might be, you can see this multiplexer and so on. These are actually needed because you might have an if statement in the middle. If you have an if statement, unless you evaluate the condition of the if, you don't know which is the next instruction to execute, right? So then you have to choose between I should go to the next instruction to execute or jump somewhere else in the program. That's also an so all of that can make it happens, and then you have to choose what would be your next, what is the next instruction. So that's the high-level view of what happens, the very basic in executing an instructions string that is coming to the processor. Now, next important thing to note is that all these processors are in a synchronous and every bit of it is clocked. So it's running a particular clock frequency. So you think of by a processor, you'll say, oh, it's running at 3 gigahertz. Right? So what it really means, it is essentially capturing the clock at which processor is clock, how fast it is actually. So if it's 3 gigahertz, you can see that it's like 1/3 of a nanosecond. It's just clock cycle, clock period, right? So what would happen typically is that in the fast clock cycle, you will probably fetch the instruction 0. The next clock cycle, you can actually decode it. The one after that, you execute and so on. And then once you're done with the instruction 1, you can actually go to the same thing for instruction 2 and so on. Okay. So this is called an unpipelined implementation. And you would not probably find any processor, including the tiny bit processors in your processor everywhere, in your washing machine, that would also not have an implementation like this. But the basic thing that people do is something called a pipeline execution. So the idea is, since these are actually clock circuit, when you're fetching the instruction, when you are actually executing the instruction string, you can decode at the same time. You can actually decode the instruction 4. Okay, so you have these units for fetching, decoding, executing, writing back. At a given cycle, at a time cycle, at a clock cycle, when you are executing to single instruction, the later instruction, the next instruction, you need to decode. So what actually happens with this? The advantage is that the latency that you would actually get to execute each instruction not actually change, because if you have like 4 or 5 stage still signals, whatever your clock period is, based on that you will have a latency. So it increases the throughput because after, so think of this situation. This is the case where things in the plan, and if you have say in 3 instructions, okay, each of them is requiring 4 cycles. In order to require 4. If you have applied it, you'll see what actually happens. Like, of course, you do not have 3 instructions, but you have billions of instructions. Initially, you will actually take, here, if there are 4 stages of the pipeline, you take like 3 cycles to fill up the pipe. After that, every cycle, you will finish one execution of one instruction. Okay, so individually they are not getting faster, but overall, since you will not be executing 3 cycles, 3 instructions, you will like executing billions of instructions. And each cycle, you would actually be completing one instruction. So pictorially, it actually looks like taken in an example. There might be an instruction, there is a load, there is an in a store. These are the addresses that we talked about. Load stores. These are actually these are the addresses on the table. It just says, oh, I need this data, I need that data. Put it on the register so that I can compute my clip. I can do multiplication, addition, and all this. And this guy is using, say, some data that is already on the register that was probably loaded before, and then computed on it. It could be actually output of some computation that has happened before. Okay. So how pictorially it will actually look like? In the first, you start with the instruction in a first cycle. Okay, there was an anyway, fine. Whatever, there was a time. So first instruction when it is in the in the second cycle, the first instruction that is excluding if it is in the in the next stage, you started to fetching the next instruction. So it actually flows through the pipeline like this. So at any point of time within that execution pipeline, there are multiple instructions that are in flight. There are different stages of computing. So this is a very basic that you do, and you can actually see some of the connect, right? If you have a faster clock than processor, if you think about the time that you require to complete execution would be actually less, right? There are limits, like you have to do some work at every cycle. If you can't do that, then there's you have to actually make sure that you finish that and have a situation that I may or may not finish. Then it don't work, right? So you will make sure that things that within that time period you can actually finish the work that you need to do. But if you have a faster clock, then more likely that you actually finish executing the program faster because your pipeline will run faster. Okay. So I think this. Any question? This is an skill. Go ahead. Only clarification question. Go ahead.
So each set of instructions that you can give, like let's say does that take only the amount of length which has been clocked by the CPU, or it can take more or less?
Yeah, good question. So the question is that there's an implicit assumption I'm actually making here that all instructions are supposed to be similarly taking similar time, right? In general, it is not true, not always true. Right? For example, if you have floating point instruction division, it will take longer. It will take actually multiple steps to complete. This complexity is the pipeline has to manage. So what it does is that if you actually have an instruction division, right, it takes in the middle, it will actually hold back the instruction that is depending on it. It will actually Right now, you need to see interestingly, I've actually chosen the instructions so that there is also no dependencies. In the real world, there will be dependencies, not not every instruction will be dependent on each other, but there will be all of that. You have to actually respect all of that. And actually, there's some called pipeline bubbles. Just like in a pipeline, there will be water bubble. There will be bubbles that has to be introduced, and those control circuits will make sure the correctness is guaranteed. That's not compromised. If you have a little less performance, that's okay. Not ideal performance, that is okay. You can't compute wrong. Okay. If you compute wrong, you blame it on the Windows, mistake. Okay. There was one more question.
I wanted to ask something.
So that's handled in the that's a stack thing. That's on the software side, it will actually manage. So what the processor says, okay, is a stream of instruction, is a sequential instruction, and what instruction maintain is that whatever you do inside the processor, the software should just think or feel like all the instruction it gets was executed sequentially. Okay. When I say sequentially, one after that, that's something that is hardware actually managed. Recursive function and so on, these are actually implemented through how we actually manage the stack and so on. This is code in the language level thing that actually happens. Okay. Fine. Now, so this is the basics. And as I say, it was actually a good question. What I was going to say is that this is an ideal world. Life is not ideal. Either. So there will be actually bubbles in the pipeline. In an ideal world, whether you are completing one instruction or completing one instruction. In a real life, it won't be. It will be actually less than that. Still, having a higher clock frequency typically would actually make your compute fast. Okay. So next part that we wanted to quickly cover is that this story about caches. Caches are very actually important in the process. So what happens is that there's a gap between the speed of the DRAM, the memory, which is like access it will be like 80 to 100 nanoseconds. Right? But it is slow. On the other hand, the registers are fast. They are at almost they are at the speed of a processor. Now the problem is there are very little of it you can actually have. So if you have large, you can't actually log them fast. So what happens is that in the middle comes this caches, which are keeping the recently accessed data so that you don't have to go to the DRAM all the time. And these are actually fast. So high level, what the caches does is exploits a general property that when you write a program, there's something called an access locality. You are likely to access the same data again and again. There are only few portion of the data that are typically 20% of your data. Most will account for 80% of your accesses. Also, there's something called spatial locality. So, what is spatial locality is that think about matrix. If you are only accessing the data, particular matrix element, this is also likely that you will access its level soon. Okay, so cache basically exploit this spatial and temporal locality to make sure that you don't have to go to the slow DRAM all the time. So if you fit in the cache, then you can quickly get access to the data. Okay, so at a high level, you have if you find something in the cache, you call it a hit. Things are faster. If it is a miss, you have to actually go to the next level of the memory and fetch it into the cache. Okay. And you can actually see that if you can increase your hit rate of the cache, so much will be better because you don't have to go to the slow memory. The point here is that you try to design a larger cache, the likelihood of it would actually go up because it's just temporarily caching. It's a temporary store, and if your store is bigger, you're likely to find what you need in the store probably higher. If you have a larger cache, the hit will actually go up. Accessing that cache will go up. It will become a detriment. You can have high increase in hit rate, but your every access would become slow. If you have a smaller cache, then your accessing time to actually access the cache is fast, but you would actually might have higher usage. Because of that, what you really do, you have multiple levels of cache. The L1 cache, which is fast but small, like few kilobytes, and it is like within 1 nanosecond. Then you have a level 2 cache, which is slightly bigger, but also slightly slower. And then you have a much larger cache, which are much slower, but also much larger too. So you first pick up the level 1 cache, then level 2 cache, and everything else. So you manage the trade-off between the latency and the capacity like this. So you can actually look at the slides later to see how this time trade-offs actually and the capacity trade-offs actually goes numbers again. One other thing to keep in mind is this whole caches and so on is managed by the hardware. This is within the processor and managed by the hardware. While the DRAM and systems and so on, you need the management operators to make sure what is there in the DRAM system. And the DRAM is something that the processor has address. This is this and the disk. Okay, and I'm not going to that. One thing to keep in mind as a programmer is that cache is very important for all of the program. As a program, programmer, how you write that program affects the locality and affects the cache behavior. If you are accessing a simple matrix, okay, you have two ways to access it. If you in an array of say each cache line, which is like typically 64 bytes, is length like that. If you are accessing that in the rows first, so then what happens is that once you bring a cache line, you access it multiple times, it will go to the next one. Your locality increases. So if you write a program which while you have actually more locality, then your performance will be better too. Same program, same functionally correct program you can write while you have less access locality and your performance will be much worse. Flashes are very important in terms of performance. So at a high level, so what really happened, what we talked about here so far is that you're talking about sequential or serial execution. What is in software? Everything you are giving a single stream of instruction, and the processor needs to actually execute these instructions. But there are many ways you can actually improve the performance. We did not talk about you actually execute the instructions out of order. You speculatively execute. Later on, if you find out something gone wrong, you edit and re-execute and so on. And you have like performance improvement to pre-pitching and so on. But there's a limitation how much you can do with the sequential or serial execution. It's limited by two things. One is every time you increase the frequency, as I said, the power is kind of in proportion cubic of that frequency f to the power 3. So the power goes through the roof. At the same time, there's a limit of how much time you can actually extract sequential program. Okay, you can do all of this out of order and all of these things, but there's a limit to it, and all of this actually has to come. So you can actually see nowadays that the processor frequency doesn't increase anymore. So almost everything at the same time, it's the same pace, because if you do that, things will can't actually increase the power. You see that in the processor specification, there is something at term called TDP, terminal design point, right? At the maximum power, which is equals to the amount of heat relation generate, it can sustain. And that is related to the processor frequency. You can check that if it's larger, if the processor frequency is higher, the TDP will be 2 to in general draw more power. So with that, what happens is that so after the all the sequential thing that we actually talked about, same software you give, you have a better processor and things start running. Now that's a free lunch for the software. And that has actually ended when you talk about multiple cores. So if you have a multiple cores, you have to give the software has to give this independent stream of instruction for a course to execute. So you have more cores, you need more parallel software to make use of all the cores. Otherwise, you might have an say 16 core machine, but you might be actually using only one core. Right? Doesn't make sense. The software now responsible to take most of it. And this actually happens because you cannot actually increase the frequency of the cores anymore without busting the power budget. At the same time, you have many registers start getting small. So what do? You actually copy it many times. That's the multi-core. High level, how the multi-cores are actually logically viewed is that each of those cores has independent pipelines. They can execute independently. But they have a shared view of memory. So what it means is that the same address that one particular core is running on a separate thread, so running on one particular core, can access another thread running in another core can access the same address. What it means is that you can communicate between them implicitly by reading and writing to the same memory address without involving network and so on. So that is possible because you have both of them have all the cores have a shared view of memory. Now the problem comes is that there is this, you have L1, L2, L3 caches. Typically, the first two levels of the cache are added to each queue. What it means is that it is use of only that particular queue. Okay. So the accesses from here would not directly go to this L1, L2 caches of the core 0, say from the core 2 to core 0. That won't happen. The problem is, then the last level is shared. The problem is that this thread might update a particular data item, address, and that would come, it would first bring it and then actually update it, and that data might be in the L1 cache. That's the latest copy of that particular data. So that something running on the core 2 might access the same address. So how to make sure that you get the latest value of that particular data? If it doesn't happen, there's a problem. Program will break. You're not seeing the latest data. That is also the responsibility of the hardware. There's a whole to work on this. This is called a cache coherence protocols. So of course we will not talk about that. But the whole protocol is a complicated final state machine that are actually implemented in the hardware to make sure it doesn't matter which code you actually run your program. You would always see the latest data. That's the guarantee that hardware will execute. There's a question in the back. Louder.
Using data
Yeah, so I don't want to get into that, and it was the intentional. So here we just think of a software thread. Software thread is just think of an independent stream of instruction. That's it. Like we talked about, that the instructions are actually going through the pipeline. Those are stream of instructions. Those are getting into this core 0 and core 2. If your question is when you buy an say Intel processor or AMD processor, you'll see, oh, you have say 8 cores but 16 threads. When those are hardware threads, we are not talking about it. You can catch me after the talk. We explain how those are different threads. Okay.
So do you mean that every core has their own individual L2, L1, and
Yes. So that's primary. Yes, those are
cores equals to number.
Yes, these are actually common. The reason is anytime there is a shared resource to try to access it, there will be a latency, content challenge. Your request will be queued behind somebody else's and so on. So like that happens with too. Like now, remember that why we wanted this L1, L2 caches. You always want a bigger cache, but we want a fast too. So if you whole purpose is to have a fast cache, it cannot be shared because then somebody else would get in front of your queue and you have to wait. That's not possible. At the L3 level, you have, by the time you have given up and say that, okay, I need high bit rate, so I'm ready to give, giving and say that, okay, I have a, I'll wait a bit. Okay. So that's a big. If you remember the numbers, I did not talk about it. The L1 cache access will be within around 1 nanosecond. Nanosecond instead of -9 seconds. And then we're talking about this will be like 3-4 nanosecond L2 cache. There's a jump to L3. It's 12-15 nanoseconds. So this is actually even larger than that, based on how big of a cache. So by that. And also at that time you want to have a shared cache because code might not have enough data to fill up a large cache. So it will be a wastage of resource. You want to pool resource, so that's why the last level cache is shared. And from the closer to the code, this will be faster and therefore. Your question. Yeah, right.
When the L1 cache on core 0 is updating the data, will it delete the previous data?
It overrides.
Override.
Overrides. Alright.
And I was so I wanted to ask if you said that L1 in core 0 will share its data into
Yeah, this guy. No, get for
core 2, sorry. Core. So is it not the same like sensory cache?
No. So the data is here. So and this code probably is writing multiple times, right? This is the reading, writing. All this. Secondly, somebody else is asking that data. So there, so there is a lot of things here. That figures out. Latest data is here, not in the here or not in the DRAM. Okay, if you go to the DRAM, you will get that still data because there is only one copy of the latest data, and that is here. There's only one copy of that latest data. And then what would actually happen is that this guy will figure out somehow magically coherence protocol. He said that the latest data is here, keep it up, and then this data will move here. The coherence protocol maintains one kind of important rule. One is that you can have only single writer at any given time. You can have multiple readers. If a particular data is shared like a code, doesn't matter. You can have copies of it in all of the L1 cache, L2 cache. Doesn't matter because it's if it is you are writing it, then in a cache it will be only one. Okay, fine. Move on. By the way, we should. If it is not something really you don't understand.
You said that only one can write, so only core 0 can update the
any point. Then the permission moves. Okay. So then there was a multi-core. Then if you actually think about this those, I think we'll be actually running over time. Those who are wants to actually go for the clip is required. That's okay. Okay. So you typically also in the row you have actually multiple CPUs as well within a single node. Okay. And it's managed by operating system. But the important point is that you still have a shared view of memory, which means that something running within one particular CPU within a single node can access the DRAM or the memory of the processor on the same node. Okay, it is slower, so you will actually pay a penalty by program will run. It is still shared view of memory. So if you wanted to go beyond it, beyond a node, this is when you design an explicit communication over the network. So you will have a net switch connecting. And so on, you will communicate over the network to get a data that you might want to just share between say two nodes. So within a node, everything has a shared view of memory. Be it the cores within the processor or across the processors within a node. Within a node, you will have two core that is managed by the office. So that's on the CPU side. Quickly go over the CPU side of the thing. Is that the amount of data that we're actually generating over the years, this is on the amount of data we're generating, is going up like anything, right? Many zettabytes and so on. So once you have a lot of data, you need a lot of compute to get knowledge out of the data. Otherwise, what's the data use of? You can't actually get knowledge out of it. You have to do it fast. Okay. That's why you need a massively parallel compute. The CPU's architecture is designed for it. Even if you put multiple cores, many of them in the node, multiple CPUs, it doesn't scale to the next. This is why it comes to GPUs. And if you again taking this speech of this what would happen is that there will be what's the PCIe slots where the GPUs will go in. One thing to remember is that the GPUs cannot exist in Ether. It needs always a host CPU to execute. So you would have this kind of board where there will be CPUs, and then you may or may not have GPUs. Okay. So now, one of the things that you might have actually wondered that the GPU is a graphics processing unit, right? It's really how you can actually use it for parallel computing. It used to be used for gaming, right? And that was the case that originally it was actually designed for. What happened is that, so if you think and gaming and so on, kind of graphics workload, thing have. Like you have an image, you like to do some pre-processing, generate another time of images. We think of the how the images are, actually pixels. They are actually bunch of pixels, right? And when you are actually doing a processing on the pixel, these pixels are the neighborhoods are independent. What you are probably doing is an identical operation on each of these pixels. And you can do it in parallel because they're independent, right? Now, around 2007-ish, NVIDIA figured out, you can change these pixels to data values. That becomes a processor, right? As long as you have a lot of data, and on those data item, which was previously pixel, now becomes a data item, you can compute in parallel, right? The GPUs just fit into that bill, and that after is that especially the machine learning, which is primarily matrix multiplication. Before the matrix multiplication, a lot of change that the GPUs can launch on it will just clean plate up, right? Because this is one is into pixels. Great. This is how the GPUs became the accelerators. Now you have different ways to program it and so on, which is the domain which you're talking about soon. Okay. So GPUs are good at identical parallel operation on the computers. Very high level. So GPUs are not magic, right? It has some ways why it actually gets so much of better performance on the parallel computer. One is called like single instruction multiplication. So earlier, what we were actually seeing that the CPU, we have a single stream of independent instructions that the different codes can actually execute. Here, what happens is that the bunch of thread, you say that all of them, you will execute the same instruction. And then you will actually go in same instruction but different data. And then you go in lost. So it becomes the parallel computing becomes much faster. You don't have to actually separately stage the instruction, decode the instruction, all of this goes up. And then since you know that you will actually execute many things, same things on different data items, many of these data items now would actually fall within a cache line. And GPUs in data science, like they are what I get right. And if it falls, set it and make it single memory access. So that's the memory coalescence. That's another key technique that it uses. This is possible because you haven't programmed while you need multiple threads doing the same thing on different. And then finally, because you have hundreds and thousands of threads concurrently running in GPU, you need to make sure that you can just use many of the memory requests at the same time. So you have a different kind of memory. They are called high bandwidth memory. It can support things like today, like 2 terabytes per second. And compare that with like a couple of hundreds max and some node and some other level CPUs. So those are the few things that the GPUs actually got. And to understand how massive the GPU's concurrency is, if you look at the latest not just one generation now, in a GPU called Ampere plus GPU, 200,000 threads it can have a single GPU. That's the one generation back. So that's the level. So it's not parallel CPU. It's a different ballgame. Okay. So that's why the GPUs are really great at parallel conversion. And at a high level, what you can remember is that to over-glorify GPUs, they are suitable for one specific task and they do not exist without a CPU. You always need a CPU to use something to make the GPU useful. Because there will be parts of the program always starts on the CPU, then can a function, say that is very parallel, you can actually launch it on the GPU, and then it will come from the CPU again. So serial parts are always executed on the CPU. Finally, a pictorial view of if you want to decide whether to use CPUs or the GPU, think the GPU as a massively parallel compute, but it is designed for throughput computing, not the latency. If you have a latency requirement, fast latency for single request, then you always have to actually rely on the CPU. This is the general purpose. You always require a CPU, the operating system, and so on will always run on the CPU, not on the GPU. If you have if-else in your program too much, GPU performance will be changed because it needs all the threads to do the same thing. If you start doing some threads doing each part, some threads doing else, performance will be gone. Okay, so that's an cautionary note, which I'll actually stop here. So I'm available in a few takeaways that you can actually take from here is that there's a limit of sequential in a or serial execution. It is important. It is very important. You can't actually live without it. There's a limit to it. Primarily comes from the how the programs are actually designed as programs. How much parallelism can you actually learn, and then the power management. Then you have this multi-cores and multi-CPUs that helps you to go up to a little bit more of parallelism. But you need GPU's massive parallelism, especially if you have this data parallel programs where you have actually multiple things, multiple data, you are doing the same operation data, and at that scale, you get GPUs. If you look at all the flops square, most of that flops come from GPU. Not only that, you can actually execute them fast, but efficient. All that you require to execute for instruction would be much lower on a GPU. At the same time, don't forget you can't just have the GPU, not have the CPU. You need that. You need the whole. That, yeah, some of the encouragements are, but with that, I can actually take the questions. Sorry for going. Yeah, but actually, he has a question. Yeah, so it's louder.
Cache.
Uh-huh.
Here, loading exclusive address. One node.
Okay. So what happens is that on the new solution. So the question was that if you are loading two addresses that are nearby, say, so then do you need twice you have to actually access the cache or get it onto the cache, or you can actually put things together? And the answer is that if they fall on the same cache block, so that each cache block, the CPU is 64 bytes. Okay, and if two addresses that you are accessing are within the same cache block, you always bring things in the cache block and the cache in the cache block boundary. So even if you requested say 4 bytes originally, the whole 54 bytes will be actually made. So that you access another 4 bytes that happens to fall in the same 64 byte region, you need service out of the. You don't have to go back to the memory. So that's the called special locality that it actually takes advantage by having a job. Yeah.
Sir, for the clock speed of GPU.
Good question. Typically, the clock speed of the GPUs are lower. So you would have 1.5 gigahertz, 1 gigahertz, 1.5, 1.6 are very common these days. The reason is, think of it, why you want to have a high clock frequency. Because if you want tense sensitivity, that is why in the CPU, right? You want to do, you have one thing that you can actually, want to do fast. What you want in the GPU is throughput. Okay. So there, how many threads you can actually execute in parallel matters more than the bandwidth of the memory. All of this matters more than the clock frequency. It does matter because latency does frequency, but the primary goal is to put things in things into the same. So the GPU clocks will be always lower than CPUs. Any other question? Yeah, go ahead.
So you don't understand why weak cache is bad. Because if cache is weak, then I understand. So that I can access it more faster. Why is it? Why?
Yeah, so because every time you access it, it will be slow. So you have so think of it like you have a temporary flow, and you can keep a lot of your recently accessed data, right? If it is bigger, then the likelihood is that you have more cache, then you find the data that you are actually looking for. So if you come there, you would have to take longer to access it. That every time coming and making every access actually, every hit slower can outweigh your benefit of hitting into the caches. Because every time slower, but you have cumulative effect, right? You're probably hitting 1,000 times in the cache. You see 10 times, and say 1,000 times in the cache and 100 times you are actually missing, right? Now you make it cache bigger, and there is a diminishing return. You might actually now have 1,050 times hitting in the cache. So this now actually becomes slower, and saving this 50 accesses to the DRAM in store, nobody is doing it, might not be getting you the overall, the benefits. There's one more question.
Synchronization of L1 cache.
Synchronization. Okay. Yeah. Go ahead. Yes.
So does that happen even on XCs or and continue issues, or is it only dependent to the system?
No, it actually happens. This question. So the question is that in coherence thing that we actually talk about how different ports are accessing their data. You have to figure out whether it happens in the HPC or multi-node and so on. As long as we are talking about shared memory, which includes multiple sockets, like multiple processors within a node, within a node, there also it actually happens. Most of it happens in HPC or supercomputer. You're buying the processors from, say, typically Intel, AMD, or it's the same processor. Okay, so within the processor, you have multiple cores. They will, make sure that all the cores are getting the same view of the memory, which means that synchronization you're talking about will now you put two processors, okay, and in the same node, or four processors in the same node, and then core 0 from say processor 1 is access some data. So that processor 3, core 10 is accessing the same data. It will also make sure the core that the core 10 or core 3 from the core 10 from the processor 3 is going to get the latest data. This is the differentiation you actually, so which means that even the processor should be able to understand that there can be other different processors. Okay. So this is the differentiation you actually do. For example, just a quick bit, if you buy an Intel processor for desktops, you will say Core I is something, right? And then you have this Intel Xeon class, which is the SATA processor. Some of the differentiations are like this. You can actually put two Intel Core I processor within the same motherboard because it doesn't understand this across the CPU coherence. If the Xeons, they understand. So all of this also you require a different motherboard. All of this differentiation comes in from the type of system that you actually do.
Does this happen over the network with other nodes?
No, that's why we're saying that it's not a shared memory. Then you require an explicit communication. As long as it is a view of the memory shared, which is within the node, and within the approximately multiple cores within the processor, as well as multiple processors within the node, you can communicate through the same memory, same access. As soon as that actually happens, you have to make sure that you get all of the latest data. So all this quote unquote synchronization or coherence is done by the hardware. Mother makes once you go beyond single node on the rack, you have network. Then you have to explicitly communicate the network. No guarantees. You don't have shared view of memory.
You have an MPI tutorial.
Yes, exactly. So yes, that will actually explain that when you go to these different nodes, what happens. Any other question?
Any question online?
Yeah. Sorry, online. I will take the online first. Any question online?
If there is, you can unmute and go ahead. If there's none, maybe we can stay on this.
What is latency value for calculated using MDAS?
Okay, so the question is, once this latencies were calculated using Amdahl's law, here it doesn't actually come into picture, right? Because what is an Amdahl's law? It says that be mindful of the sequential part of your program. So what it says is that if there's a small part of your program that you can accelerate, it doesn't matter how much you accelerate, if it is not a significant portion of your program, in the sequential part will kill your performance. That's a problematic view of things. This latency that we are talking about is a hardware latencies. Like you design a system, you have designed a processor, how will it take structured access it? Nothing about program view of thing or overall program performance. Yes.
Is it that GPU is only good for tasks in which parallelism comes in? This big data which has to be just updated time to time, for example, pixel updation.
Read and so yeah, go ahead. Accommodation.
Yeah, so if the code is branched, means if there are many if-else statements also, then it is not good. So can you give an example instead of pixels in terms of GPU where it will be used?
Yeah, so if, for example, we just take an example, like take your favorite matrix relation, right? It's what the computation is. The different form of the other tensor computation. You have multiple different data items on which you can actually compute. GPU is great for that. You just like race through it because you actually compute all of them in time. You saw the level of confidence. Like it's not, it's not it's a different order of magnitude compared to the CPU. So it's not equivalent to a CPU, parallel CPU. No, right? So that's the kind of thing. And then you have to have this ability that you're executing same on a different task. If that doesn't happen, even if you have it won't be great. There are other limitations which we can't actually go into details here. The memory access is also basic limitations are like you have to have an which is kind of structured. You are accessing doing the same computation on millions of different data items.
Like simple for loops and stuff,
and then for needs to be like really wide, big. Okay. Any other question? Yeah, go ahead.
Why not see?
Good question. The question is that how many levels of caches you typically have, and why not have an infinite number of caches, right? So everything has a trade-off, So think of a data that is not in your cache you are accessing for the first time. So every time you look up a particular level of cache, you incur some levels. So deeper your cache identity is, your worst case, which is going to the data, become worse because you have to look at the cache. You're checking your locals in a place. Then, it's not there. Going to the next one. It's not there. All these latencies are adding up. And there are applications which has relatively less amount of locality. It's called skimming applications and so on. If you put too many levels of cache, they'll be pretty bad. And how big of a cache you can have is determined by the, you can't have a really large cache. There is also limitation of the registers, how many you can put it in your processors and so on. Any other question? Yeah.
There's also this trade-off between general purpose processors versus like processors specially designed for one kind of task. Generally, companies, look at the big market. What is the big market demand was, and then sort of design which is a very general purpose processor. But like for niche applications, people actually design architecture which is also like very good at doing that kind of thing.
There's many examples of that. If you Google's TPU, it's professor processing, it's right? What they figured out, look, there's economics playing into this too. So they figured out that a lot of our applications that we actually run through these fancy things as a processing, they're actually doing this application, right? And they said, like, you know what? If I design a processor just for that, I don't have to worry about this cost of generating. There isn't cost to it. Like, take care of all the corner cases. You have to do in the CPU. But if you know that you have an important use case for a single thing, you design a processor for that because doing anything on the hardware is much faster than doing it in software. You can do the same thing, but you actually do it on the system. But more importantly, It's also energy efficient. The data centers burn a lot of power. Right? It's important for the climate as well that you have efficient computation. All of this goes in. I also mentioned there's the economics to it. The reason is that if you have your own thing, then you show that, oh, I'm actually creating this own thing, NVIDIA can surveil it and then this something, right? If you have a stronger enough competition from, oh, this is recorded, I don't have to say it. Yeah, you want to change, because there is a limitation. I consult for AMD too, so I can't. Yeah.
So,
Take it on.
maybe I'll take a final question before we go for tea. What does this all mean for users like us? HPC used for scientific computing and the biggest clusters and supercomputers that will become available. Will they mostly in future almost all be GPU heavy machines?
Yes, very likely. Most of them would actually have a very GPU heavy machines. And if you look at the list of G, find that most of their flaws are coming from the GPUs. So one of the things, since you mentioned, the fastest computer today is a Frontier supercomputer. So when I was back in US during 2014 to 15, so there was part of the research that it got installed now. Part of the research was actually done in steps, and I was associated there. It was I'm proud to be that, like, being involved in that. So yeah, next computers, supercomputers, you will have heavy-duty GPUs, not only for faster computation, environment.
So the software has to keep up. You have to write GPU codes.
Exactly. One thing though is that many of this you have libraries for. You need to know functions to actually use. Because if you think of like if it is a special purpose, there are limited set of things that you can anyway do. So there's a good to it is that you can actually hand tune some of the library functions to actually take advantage of a particular picture, and then the program you can actually express it as long as you know what which library functions most efficiently on that. Those are questions. I don't know. And I don't think this is too close. That like not different people will give a different answer. But I don't think like it's not like it will come and everything will be changed and so on in next couple of years.
I think we should now move on for the tea. Let's thank